welcome everyone. Yes, Cleaning and value-based metal. I've been with Valley for a bit more than a decade now, both in operation engineering, but I guess most recently I've been leading our tech and innovation for mining, and even more recently I've moved to a more fleet strategy role within the company. Maybe Mark, over to you.
Sure. Great. Thank you, Cedric. Mark Sawyer here. I'm Vice President of Mining with Stream Systems. I'm a mine engineer by background. I think I'm one tick away from 30 years in the mining industry. Worked in a variety of roles, operations, engineering, planning. For the last 10 years, I've worked in the realm of technology, digitalization, alternative energy sources, and I've been with Stream for several years now, focusing our simulation capabilities on those very areas as well as operations.
Thank you, Mark. On my side, and I'm Michel, I'm with Stream since 2.5 years, or 2.5 years, sorry. I have a background in electrification, automation, and software development, focusing in innovation since a good 10 years in mining. I've been part of GMG Electric Mine Steering Committee since 2016, and I've been involved in several electrification projects and studies around the world. Prior to kick off the webinar, I would like to share some context. Mark, could you please just move the slide? Yeah. Then I just would like to bring some context on the energy transition. The energy transition is in very early stage. The ambitious effort to reach net zero emission is moving. However, the pace of this energy transition fluctuates yet based on some variables. The end goal of the energy transition was outlined in the Paris Agreement. That was in 2015. In our industry, Scope 1 and Scope 2 emission account for 6% of the global greenhouse emissions around the world. And this value raised to 30% if we are counting the Scope 3. Following analysis across the mining asset executive around the world, made a clear engagement around 2020 to reduce emissions in the mining industry. Generally, we can agree that the reduction were foreseen in two steps. Scope 1 and 2 were reduced or will be reduced by 30% in 2030, and the end goal is a net zero by 2050. From these commitments, we got access in addition to annual financial report, we got access to the ESG reports or sustainability report for the mining company. And mining companies was really starting to engage in 2021, 2022 to look at what they will need to do with some, I would say, experts around the world to really build a roadmap to move the emissions into the 2050 end goal. Then, as usual in mining, we got some early adopter. Then we can see that I think it was in 2018, Boliden start to stress test trolley system. Today they are testing other technologies. We saw that Anglo built a hydrogen pilot truck. Teck more recently was trailing on-highway battery electrical truck. Fortescue is really committed with a global initiative, and we have a lot of tier one companies who are today testing some battery electric haulage truck around the world. I mean, we have in Canada, we have in US, we have in Australia, and we have also other customers or other mining companies, sorry, testing IPCC pilot projects. IPCC stands for in-pit crusher conveyor, sorry. But the electrification is not the only solution. I mean, we can see and we can foresee that biodiesel, renewable diesel, ethanol, dynamic blend, hybrid are all great opportunities. And energy supply could be a major challenge in the years to come to scale up the above mentioned technology across the world. how to navigate the challenges of the technology readiness, the commercialization, and company commitment in the short term. This is the real transition within the transition that we are living in. Outside full electric, do we have technologies able to support 2030 emission reduction goals? The clock is ticking, and I will let Cedric to introduce the project that we with Valley we run together in collaboration. Cedric.
Oh, thanks, Michel. Thanks a lot. I guess just to kick things off for those who are not maybe fully familiar with valley-based metal and what we do and where we operate, just a quick reminder here. So we're basically a base metal company. We produce nickel and copper. And you can see here on the screen the various regions where we operate today. I would say we're mostly focused in our Canadian operation, where we have a fully integrated flow sheet from, I guess, underground mines up to smelter to refinery to produce nickel and copper. And our Brazilian operation, which are actually mostly open pit and the main topic of this discussion tonight, that mainly produce some of the biggest copper mine in Brazil for copper, produce copper concentrate, as well as some nickel operation. Without forgetting some of our refinery in UK and Japan and some minority stakeholders that we have in Indonesia. Next, Mark. So, and Michel, I think you introduced fairly well the topic tonight. So Valley, like many of other mining companies, I think we're fairly conscious of our climate impact, and therefore we are, I guess, committed to the Paris Agreement, which means that we've set some target for ourselves, I think back in 2020, 2021, to reduce our emission by 30% in 2030 and being net zero by 2050. However, I would say the year has passed and we're now in 2025. And I guess I like how you put it. The clock is ticking, so there's definitely some urgency now because basically 2030 is almost in our 5-year plan. So that's our current situation, our current context, like actually many other, I think, on this call. Just to give an idea as well for people on the call that basically our emission mostly coming from our refinery and smelter, actually, that uses coal as a reductant. And mining for us is around 20% of our emission. And within that 20%, I would say haul trucks are basically 60-70% of that total. So our haulage basically represents that 15% of our scope 1 emission. And it's basically top 3 emitter within the business. So something we have to tackle, and that's material. On the other side, we've got, and I guess you mentioned it, and you can see the picture here on the slide, but we've got a range of technologies. I would say most of those are in development right now. Michel, you mentioned some of those, but there's none that's been, I guess, we haven't found the silver bullet yet, and nothing that's been fully adopted. So there's still a range of options available in the future. Still lots of technology in development, so we have to make some assumption. And so that's where for us the point is really how we could navigate this uncertainty, navigate those multiple pathways, and how we can make informed decision about what we have to do and what we should be doing. Mark, yeah, if you don't mind, thanks. So really the work and the need on our side was a way to can assess all of those multiple technologies. So to be very simple, we've got some mines, we've got a mine plan, we've got an existing fleet on those mines that have certain performance, a replacement plan. And on the other side, we've got a range of technology options. And again, we need to understand, based on that, what would be the best combination for us. We need to understand what would be based on the different technology, what would be the output, what would be the cost of those different technology to implement, what would be the timeline that we can implement those as well. Nothing will happen by, I guess, snapping fingers, so things will take time. So we need to understand all of this. And at the same time, and that's maybe where the work that we did together was meaningful for us, is we need to have certain characteristic. We need to have a certain level of trust in terms of being able to model those different scenarios. There is a multiple, again, pathways and scenarios, so we need to be able to run multiple scenarios. We need to be able to update those fairly quickly as, I guess, inputs are changing, technology is changing. There is uncertainty around some of the assumption. I mean, some of the technology, we need to really model them from first principle, and we don't have a lot of historical data on those. So we need to be able to model that uncertainty among those technologies. Next, Mark. And so I guess will be my last slide prior to hand over to Mark, but that's where looking for the right tool, I would say, to do this work. And that's where more like kind of agent-based simulation we thought was a good way to approach the problem. Being able to get that sense of trust that we need, being able to calibrate, validate with existing historical data, and being able, I guess, as you can see on the bottom of the slide, kind of ticks all of those boxes in terms of run those scenarios and run those sensitivity, as well as model those technology from first principle. So that's really kind of the need and the approach that we've taken together. And I think now I will hand over to you, Mark, to get us into the meat, I would say.
So I'll start off with where we're at in terms of how we approach simulation, and the background for Stream Systems is we're a late stage commercialization company that's been doing simulation for close to a decade, and as Cedric highlighted, we focus on agent-based simulation, and that has a benefit in modeling mining operations, particularly load and haul, which I'll describe in a little more detail. The process that we use to approach any simulation project based evaluation is using a process that's very similar to the plan, do, check, act cycle, which is a standard business improvement process in Lean, where you come up with an alternative or a scenario, you test it, and you measure the results. Now, what simulation gives you is the ability to do that through the use of a simulation twin without impacting your operations while you're doing the testing, the do and the check part of the cycle. The way we do this is through construction of a simulation twin. Now, this is done where applicable and practical. We apply historical data to construct this simulation twin. We do this through deployment of operating data, such as fleet management data at a mine site, where we're able to learn from this past performance and your operational behaviors that exist and are present in the data, and use that to help predict future performance. This is done by applying data science and machine learning to that operating data, and it helps us create a high fidelity simulation twin that reflects the performance of that load and haul system in the context of the current operating environment. From that simulation twin, we calibrate a model to a defined period and measure its performance against a number of operating metrics and work with our stakeholders to confirm that we have in fact validated the simulation twin and it's performing as your operation does within tolerances. From there, we progress to a reference case. So it's a point in time that then we're going to measure scenarios against, and this includes taking the established operating performance and behavioral profile that we've established in the simulation twin, establishing that in a reference case, and measuring the results of our scenario analysis against it, and then from the scenarios, we move into action and assessment. Now, what does this mean in terms of how a multi-agent simulation works? In simple terms, multi-agent means that each operating asset in your mine, in your operation, is represented by an agent in the simulation model, and each of those agents has its own set of configurations and rules that dictate how it will interact with other agents. So loading units act as loading units, trucks act as trucks. And within each of those, they have their own specific configuration. So trucks of different makes and models each operate as per their characteristics, and if you have different makes and models of trucks and loading units in a mine, they all adhere to their own operating performance. What makes multi-agent simulation powerful is that we're able to use that historical data set that I talked about to establish that baseline of operating performance that the model uses. We're able to represent the mine road network in your 3D operating environment at the present or any historical or future period to represent different baselines or of operation. And representation of that load and haul operation is as an integrated system, and all of those assets are interacting with each other, and you're really modeling it as a system, not as a bunch of individual haul networks that are linked. So all of those individual agents are interacting with each other. And this style of simulation, for comparison, was used, for instance, during the early days of COVID when they were modeling how, the disease could spread amongst populations by representing people as agents in a model and how they move and interact with each other. Similarly, a load and haul fleet has an infinite number of interactions that can happen based on the number of units in the mine, and each piece of equipment is represented and all of the interactions represent the performance of the system. We can test this by adding, removing, or replacing individual agents or assets within the model and measure the impact on the system. So we can remove a truck or add a truck or change the characteristics of a truck and take the engine out and put a battery in, within first principles constraints, and see how that impacts the system. And that's what gives us the ability to evaluate fleet decarbonization initiatives and evaluate it across transition periods where the nature of the fleet is mixed for a period, and the performance of that mixed fleet can be measured over time. Now, configuration of the agents is critical, and enabling us to look at this across a number of decarbonization alternatives is critical. So I'm going to show a quick video on how we configure each individual truck with the maximum flexibility to look at different energy systems, including battery electric systems, alternative fuels, completely alternative systems such as hydrogen systems on trucks that involve dual energy sources. So our ability to configure to match different energy configurations is critical for us. Now, what we're looking at, and I'll just pause this and ground everybody in what we're showing. Now, we've just created a hypothetical Hall cycle that's shown on the top left of this figure. So you can see there's a Hall cycle that goes uphill, downhill, and then back up to the loading area. And after it's loaded, it'll go down and follow the same cycle. Now, what this truck configuration shows is there's multiple possible energy inputs, and there's dual possible energy sources on board. There's two blue bars in the middle of the truck. The top one represents, in this case, we're showing a diesel electric hybrid. So this is a diesel truck with a battery on board with a closed system. So it's not a plug-in hybrid. All of the energy in the battery is sourced from regeneration during downhill hauls, where the retarding capability of the truck is captured and put back into the battery. You'll see that there's two external sources on the green lines. The top one is for a trolley input. The one out the back is for a static charge input. Both of those are disabled in this specific scenario, but those are we have the capability to enable that. So we could rerun this scenario, enable trolley, and install trolley in part of our haul route, and collect energy dynamically for the charge of the battery during haul. That's not how it's configured for this haul. And then we also have the diesel tank, which is at the bottom blue bar, and you can see it's about 2/3 full of diesel at this time. The graphs on the right side represent the elevation across the hull, the velocity, the current energy consumption or regeneration. So consumption is in red, and when we get to the regeneration portion of the hull, you'll see that it turns green, both on the hull and in the graph, third from the top on the right. And finally, we have acceleration at the bottom, and you can see as the truck pulled away, it went through the gears, and it's proceeding onto the flat section of the hull. Now I'll let this go and take note as it goes up the hill. The state of charge on the battery is going down quite rapidly as it consumes the battery energy. Now it's heading into the downhill portion of the hull. It's regenerating, and the battery is gaining power. Now it's back into the flat hole and uphill to the loading area. Again, it's drawing that battery down, and it's almost at zero. I'm going to pause and just explain how the system is working, that it's configured that when there is battery capacity available, it preferentially draws that battery capacity down. And when the battery capacity is spent, then it goes back to diesel power in its entirety. We can reconfigure that to blend diesel and battery power on any kind of substitution curve you want, but in this case we kept it simple for illustrative purposes and showed that the battery is drawn down. So now the truck is loaded, going downhill again. It gained some charge, but not enough to sustain it. So now it's going uphill and the battery is depleted, so it's entirely on diesel power as it goes up the hill, the final hill on its way to the dump destination. It'll crest the hill and then gain some regeneration on the way down, but not enough for meaningful charge. So what we got is, based on this hull profile, there's not enough downhill hull to really gain a sustainable level of charge in the battery. It provides you a bit of benefit overall in the net energy composition of that hull profile, but it's mostly running on diesel with a bit of help from your battery. Now we're going to rerun this with the scenario of zero rolling resistance. Again, we all know that that's not practical on a mine site. The objective is really to show that if we theoretically went to zero rolling resistance, what would that do in terms of providing us more regenerative capability across that hull profile? You can see there's a lot more green regeneration happening when we go to notional zero rolling resistance, and the state of charge on the battery gains a significant amount across the hull. Where we get to the loading area, it hasn't depleted. We have about over 50% charge, and it's enough to sustain it across the hull. So we can see in this scenario how the significant drop in rolling resistance enables the truck to gain a sustainable charge on the battery and enable it to run most of that hull cycle on battery capacity as opposed to powered by your diesel engine. So that's just an example of how we configure each truck independently with its own energy system, and it's configurable in multiple ways to have multiple energy sources on board, the ability to draw different energy sources externally, static or dynamic charge, and the ability to dynamically substitute a secondary energy source for a primary energy source. And each of those configurations is unique. So you can have a fleet that's all configured the same with the same energy characteristics, or we can have different energy configurations across different parts of the fleet. So we could have, in that case, diesel trucks running mixed with a hybrid diesel portion of your fleet configured the way we showed it, and we could convert some of those hybrid diesel electric trucks to have a trolley on them and collect energy dynamically from a trolley system if that was available. Now, with that explanation of how we construct our model, agent-based model, the next piece is to build our design of experiment to evaluate various scenarios. And these scenarios are all compared against our reference model that is used to give us the ability to compare specific metrics and key performance indicators and measure differences between that reference model and various technology states. So we base our design of experiment to model our fleet based on what technology do we want to evaluate, what energy sources are we going to use for that technology. Are we using diesel, alternative fuel sources? Are we using electricity, site-based electricity, or regenerative power on the truck, or a combination of those? How does our site perform operating as a homogeneous fleet or as a mixed fleet as we're moving through transition? And where do we place key infrastructure to support these different technologies? So where do we put fuel stations? Where do we place charging stations for battery electric fleets? And where do we place trolley systems for dynamic charging of battery electric fleets? This helps us identify what are our key value drivers for these scenarios. Is it infrastructure based? Is it based entirely on the technology? Are there constraints that are coming from the technology itself, or the mixing of fleets with our base fleet? We want to measure this based on the impacts on the fleet itself. How is it performing? What's our productivity, and what are the implemented delays and new events that are introduced by adopting these new technologies, and how can we mitigate the impacts of those introduced delays and events? We also want to determine on a period by period basis, have we become more truck or shovel constrained in these various periods? Do the trucks speed up? Do they slow down as a result of the technology? Does this mean we need to modify the fleet size to achieve our material movement objectives? And finally, how does this impact our site energy usage? Our electricity consumption, where that's relevant, and what are our emissions profiles from the various scenarios. The additional dimension to this is looking at it across multiple periods. So when we're looking at multi-period analysis, we want to establish a baseline to compare against for each of those periods, and understand what does our transition or fleet makeup look like for each of those periods. So typically, we're starting with some kind of diesel fleet that may be homogeneous or mixed to start with, and you're matching your decarbonization technology initiatives with the transition of that fleet. And we're looking at that transition as it happens across multiple periods of the mine plan, and we're able to measure the impact across each of those periods. That's done by ingesting the mine plan, building a representative road network, and operating characteristics for each of those planned periods based on the mine plans that are provided. Now, the next few slides are illustrative and to show typical outputs from this type of analysis, focusing on operational impacts, energy and emissions impacts, and financial impacts. So this first one, again, just illustrative to show the ability to look at these scenarios in detail. This one looks at the impacts of a load and haul system by implementing battery electric trucks with and without trolley systems, and with decentralized static charging systems. So the three bars on the left-hand side, it's a battery electric system with 6 total charging stations, and the bars represent total ton movement, and then the secondary measure is our fleet productivity. The next one over is the 6 centralized charging stations with trolley removed, and you can see the decrease in total mine site production. And finally, it's trolley back in, but our charging stations are decentralized, so we distribute charging and reduce it to 4 total stations, 2 bays each. So you can see the difference in total mine site production across these 3 scenarios. And then on the right, you can see, breaking it down further, how the time that is lost when we reduce the trolley is lost in our time usage, that we spend more time queuing at our energized unit, we spend more time energizing, and we also spend more time traveling to our energized unit. So that's where our time is lost when we remove the trolley from the scenario. And in the case where we decentralize the static charging, we also have an uptick in all of those metrics for waiting at our energize unit, actually energizing, and traveling to our energize unit. The next one is also illustrative on evaluating energy and emissions across multiple scenarios. So on the left, we have a typical energy profile that is provided. Now this is over a typical shift, where the orange portion of the figure is electrical energy from dynamic charging or from trolley, and the blue portion is electricity from static charging. So you can see the majority of the power in this scenario is from trolley systems, and it's supplemented a little bit by static charging. But the key here is the significant difference between peak and average power. This is an unconstrained model, so we also have the ability to constrain the power on the model and evaluate how that impacts fleet performance. This one was unconstrained to look at worst case power impacts on a mine site. On the right is a number of technologies evaluated from an emissions perspective over multiple years. So if you can't see the x-axis, this is evaluated from 2026 to 2037. The first point here is the dynamic ethanol blending. So this falls kind of in the middle of the analysis in terms of emissions mitigation. It gives you moderate mitigation that's in line with running diesel with trolley systems and hybrid diesel electric systems. Now, what you see is the ethanol, based on its dynamic blending, as you have more uphill loaded hauls, you have a higher substitution rate, and your emissions profile goes down relative to your other cases. So you get more benefit as you go deeper and have more uphill loaded hauls. Diesel with trolley, as I mentioned, is also in that same range, but it trends up and follows more closely the amount of uphill loaded hauls you have as you still consume energy on those hauls. Then we see our renewable diesel, which that's a drop-in solution available today if you can actually find it and procure it. So you can see it's rapidly implemented and provides extensive benefit based on the emissions profile that was attached to that renewable diesel, and sustains that performance over time. And finally, there's a number of battery electric cases with and without trolley that fall from the kind of the mid-range of emissions mitigation right to the full retrofit of the fleet, which gives you virtually zero emissions by the end of this evaluated period. Also note that these battery electric scenarios follow a more gradual ramp up over the period. And then finally is the economic evaluation. So on the left is looking at operating costs over 2 periods, early in the transition, late in the transition. The bottom part of these graphs is your diesel and related costs. And then at the top is your maintenance and repair and other operating costs. If we go to the right side, that's later in the transition, this is highlighting the renewable diesel, where a very high operating cost was attached to that renewable diesel that really drives the cost of that mitigation. Next over, I'm highlighting the ethanol case, where the ethanol provides you mitigation, and it gives you a pretty flat operating cost scenario relative to your diesel. And then finally, over onto the right, we have our battery electric scenarios, where that bottom pink section is your electricity costs. So at this site, a very low electricity cost per joule of energy relative to diesel. So significant OPEX benefit there. And the battery replacement or battery management costs were at the top in that pink and green color, and with a key difference between different battery chemistries driving the cost based on the replacement cost of those batteries and the number of charges between replacement. And then finally on the right is our marginal abatement curve, which looks at the cost of mitigation relative to baseline and the absolute amount of emissions mitigation relative to baseline. And note that on the far right is that renewable diesel scenario where it had a high level of emissions mitigation, but it came at a high cost. So this measures the two in combination and allows you to compare these scenarios head to head. And then finally, to wrap up, what does this mean? And I'll let Cedric describe a little bit in terms of what this means to Vale. But this is really about the action taken from these types of insights. In the case of fleet decarbonization, there's multiple actions taken towards, screening your alternatives, narrowing your focus, managing your risks as you move through this journey, looking at your potential financial and economic impacts as you move through your internal decision gates and frameworks. Simulation can aid you in all of these and allows you to really focus the outputs and the insights on the different audiences during the different points along the journey, and allow you to reevaluate as new information comes available and make those changes without significant model reprogramming or reconfiguration. Over to you, Cedric.
No, thanks, Mark. Hey, try to leave some time for question, but maybe key message to conclude here is, first of all, in terms of the tool themselves, I think that those are the tools that I think as an industry we should really be using, and that's a good use case. At least for me and for us, being able to model all of those different technology from first principle, as you've shown, being able to run those different scenarios with different fleet composition over time to really kind of have a very operational schedule, not something that's maybe black or white, but very something that we can see the mixed interaction and understand the behavior, as well as being able to run those kind of sensitivity on the key parameters to quantify that uncertainty that goes with that new technology, right? So I think that's a tool, I think, as an industry and using simulation, that's a good use case for that. In terms of what we learn and what we'll do next, and again, I will try to keep it short, but based on what we've seen again, and spent actually a quite fair amount of time about getting input to those model, talking with different OEM, with different vendor about the different technology, and achieving the 2030 ambition with the current state of technology from what we can see would be challenging, because again, not all this technology would be able to be implemented in a day. So I think in a realistic scenario that would be quite challenging. And therefore, we also have a need for, I would say, a pragmatic approach, and some of those transitional solution, and I guess we mentioned, and it was in the graph, but things like hybrid or alternative fuel like ethanol, that can be retrofitted on existing fleet. I think those are some of the solutions that maybe actions that could be taken here and now, and don't wait for later. In terms of what to do next, I think this is very hard engineering here, but I think we need to evaluate also this in conjunction with some non-financial criteria. So supply chain is one, for instance, that we're talking about, like HVOs as an example, or renewable diesel, operational risk as well as we talk about like newer technology. So this is, I would say, again, the hard engineering, but we also need to understand the other criteria that goes into it and understand what would be the option for us to de-risk our plan moving forward. I don't think it's only a one solution or one bet, but we need to have several bets and hedges to de-risk our plan and be able to meet our goal in the future. And again, I will try to keep it short and sweet here for question.
Thank you, Cedric. On our side, I mean, first we would like to thank you, Valley Base Metal and Cedric and the Valley entire team for the work that we done together. We want also to thank GMG for today's opportunity, thanks the two other. Then we are at the beginning of the energy transition. We need to understand new technologies interacting with existing fleet in a defined mine plan, and we are at that step, right? Simulation, twin, software, these things will evolve over time. We are working on different time horizon. I mean, with Valley and what Mark shown you today, we have been using past data. I mean, for the archive data, I would say from that specific site. Tomorrow we will ingest live data and provide optimized scenario, and that will continue to bring that transition within the transition to support operation live, part of the energy transition and the integration of, as just Cedric said, new retrofitted technologies within the overall mix of existing fleet on that specific site. Then I mean, it's a lot of things in front of us to be able to be successful as a mining industry player all together into that transition. But I think we are all very confident to be successful into that, and hopefully that today you learn things, and I will now hand over to Heather for the next portion of the presentation. Thank you, Heather.